Hello everyone, welcome back in the course of Earth surveying, and today we are in the new module called Time and Astronomy. This is module 3. Before going into this module, I would like to summarize learning of last module. In the last module, we discussed about the terrestrial reference system, reference frame, coordinate system and other aspects. We learned that there are some reference systems and reference frames required in order to define the 3D position on the surface of Earth. And so we defined three reference frames: local reference frame, geodetic reference frame and geocentric reference frame. All these frames are non-inertial frame, which means they are also rotating with the Earth, or rather they are attached with the Earth. And as a result, we said that we do not need to measure the time. Suppose now you believe or you realize that we also need one inertial reference system and inertial reference frame, so that we can also locate the position of a point on Earth with time. That means I need to measure the time also, time and 3D position together. So this module has 4 lectures, and in this lecture we are going to talk about fundamentals of astronomy. So these are the books one can refer. Let me tell you what is astronomy. Astronomy is the study of motion of heavenly bodies. So what are these heavenly bodies? What do you mean by heavenly bodies? So all the stars which are appearing to you in the night, if you are going to your rooftop or if you go to an open ground. So these stars, including sun, moon, they are called heavenly bodies or sometimes celestial bodies. So we are studying the motion of these stars, and we call this science as astronomy. Let us go into the astronomical reference system. It is slightly different from the terrestrial reference frame in a certain way. Just imagine if you go to the rooftop of a building, or if you go to a cricket ground or football ground or hockey ground or any open ground, if you can avail and if you can go there, go in the night time, you will feel that the sky which is appearing black to you, having a lot of stars on that. Well, it is not surprising, right? So have you ever seen the black sky or the stars on the black sky? There is another feeling if you go in the daytime, if sun is not intense and there are no clouds in the sky, then you can see the blue color of the sky. If you go in the evening, or if you go any time when there is no sun or sun is not that intense, and go to the open ground and try to see around you, you will feel that there is a sphere that is surrounding you. In the daytime, it is appearing as a blue color sky, and that is basically appearing to a half sphere, and which is like that around you, and that is what we call as celestial sphere. Well, in the night time, this blue sky will not be there because it will not be visible as blue, but still there is something, and we can see a lot of stars around us. Okay, surprisingly, you may feel that a star which is appearing bright to you, perhaps it is closer to you, or a star which is little dull, it is away from you compared to the bright star. Sometimes you feel it is a big star because it is appearing little bigger to you. But do you know that even with your naked eyes, you cannot measure these distances? Secondly, even you measure those distances by your naked eyes or by some instrument, they are of no use. Why? Because even we know the star's distance, what will you do with that calculation? So we assume that there are stars which are situated on a celestial sphere, which is appearing to me as a hemisphere around the surface or around my position. Okay, and then we say that okay, let us assume these stars are situated on the surface of the sphere, and the sphere is of infinite radius, and because of that infinite radius, I cannot measure the distance between two stars or the distance between a particular star and the observer. Suppose if I am standing on open ground or you are standing on open ground, then you feel that okay, this star could be nearer or another star is farther to you. However, you cannot make the difference between the two because all stars are situated on a sphere that has infinite radius. Well, what is this idea? Why are we making this assumption? So, we are basically interested in two angular positions. That means we are not interested to measure the distance of a star to star or distance of a star and observer. So, that is the reason we are making this assumption. But if you imagine the Earth, which is at the center of this sphere, and the whole sphere is around it, so you can imagine there is a whole complete sphere. It is not a half sphere anymore now. Well, that is what we call celestial sphere. I hope that I have repeated this concept many a times now. Okay, so all the heavenly bodies like sun, moon, or any star is appearing as situated on the surface of that sphere. The observer's eye is the center of that sphere. Well, you can ask, why is it so? The idea here is, when I assume that infinite radius sphere around me, the radius of the surface of a point on the surface of Earth, which is approximately 6400 kilometers, does not mean anything. Why? Because compared to the distance of an observer to the celestial sphere, which is almost infinite, 6400 kilometers does not make any sense. So, even I can assume that the observer is located at the center of the Earth, and he can direct his eyes like this to visualize two stars, or he can make the difference. There is one star and there is another star, there is a lower star, there is an upper star, like that. So, all the differences he can make, but still the distance between this position and the star's position cannot be determined. Well, I hope that we are now getting involved in the astronomy. Okay. So, the idea is the all heavenly bodies are moving relative to the Earth, but most of the stars which are far away from the Earth, they might be moving, we do not know, but at a given time, let us say 8 p.m. in evening, if I go every day, I will find their location remain fixed. So, such stars are also known as fixed stars. So, remember in general that all the heavenly bodies are moving around the Earth because Earth is spinning around its own axis. Now, Earth spins about its own axis in a counterclockwise or anti-clockwise direction. Because of that, all the stars, maybe sun, moon, or any other star, all they appear to move around the Earth in a clockwise direction. So, let us say Earth is moving in this direction, for example, like this. So, all the stars are moving in a clockwise direction. Fine. So, that is the idea here. So, all the stars are relatively moving if I assume Earth as a stationary. Now, I can say here one thing, that we know that Earth rotates in 24 hours, or Earth completes one 360-degree rotation in 24 hours duration, what we call a day. During that day, I can say that if Earth is stationary, all the stars which are around the Earth, they will rotate and they will complete one 360-degree rotation, or they will complete their 360-degree rotation in 24 hours. Is it not a good idea to understand the time and astronomy together as a combined concept? Because astronomy is the science of study of motion of the heavenly bodies, and I am saying that now heavenly bodies are rotating and they are completing one rotation in 24 hours. So, time and astronomy are connected. And let us start from the celestial sphere again. So, here I am showing you the Earth. Let us assume that Earth is an ellipsoid, and the blue line is rotation axis of Earth, that is joining the North Pole and South Pole. Then we have a green circle which is equator, okay, and then we have a dotted line which is showing the Greenwich meridian. This is what I am showing you here. Okay. So, you can see North Pole and South Pole, and so line connecting the North Pole and South Pole is the rotation axis of the Earth, and assume that it is an instantaneous or it can be an average rotation axis. So, you assume that it is a fixed rotation axis. Well, with this, now let us see, these are the stars shown in the yellow color. So, I am showing you here 4 stars. Okay. Let us see, there is one more star what we call Polaris, which is exactly above the North Pole. Okay. If someone goes to the North Pole, Pole star will always appear exactly above the North Pole. and it will remain stationary with respect to the Earth. So, this is Polaris or pole star. Okay. These stars which are shown here in the yellow color, they are appearing to me as rotating in this circle. They are spinning in this circle around the Earth in the clockwise direction. Now, you can make out what is the clockwise direction here right now. Okay. Could be from here to here like this. Fine. If I project all these stars on a sphere, so then they will be appearing as if they are situated on the surface internally on a sphere. So, what I am doing, let us say there is a star like that. So, there is an observer, I am connecting the star here and I am projecting it back to the sphere, such that all the stars are appearing to me on a sphere, and that is what we call the celestial sphere. Okay. So, I have placed all the stars on the celestial sphere because I am not interested in the distance between the two stars or the distance between observer and a star. So, distances have no meaning for us. Hence, we can place every star on the sphere, whether it is really lying on the sphere or not, does not matter, because we are interested in only directions. So, we are basically placing them on the sphere. Okay, let us go ahead with that. So, now this is my celestial sphere. Okay, so let us remove the circular path of the stars because I have already placed them on the celestial sphere. So, even they are moving on the celestial sphere. If I extend the rotation axis meeting the north pole and south pole of the Earth, so if I extend this axis, it will be passing through the Polaris or pole star. So, this axis we call axis of heaven. This axis is cutting the celestial sphere in 2 points. The first point, which is above the north pole, it is called north celestial pole. In bracket I am writing it NCP. In further slides we will always write it NCP. Similarly, below the south pole, the axis of heaven will intersect the celestial sphere in south celestial pole. So, they are basically not north pole and south pole of the Earth, rather they are the poles of the celestial sphere. So, when axis of heaven intersect with the celestial sphere, it created 2 points called north celestial pole and south celestial pole. I hope we are together and learning astronomy. So, let us see, there is a surface of the Earth. On the surface of the Earth, there is a point P here shown by a red dot. Okay. Let me draw the horizon. Okay. So, this is the horizon. Now, you can imagine at this horizon at point P, if you are sitting at point P, you can see few of the stars are visible to you and few of the stars are below the horizon which are not visible to you. Okay. Let us go ahead. So, it is, I call it horizon, it is observer's horizon. Now, observer is sitting there at point P. Okay. So, this is my gravity line or the plumb line passing through point P, and so it is cutting at 2 points on Earth. Well, one point we know that where the observer is standing, and another point it is just below down across the equator. Now, see that if I extend the observer's horizon, it will be intersecting with the celestial sphere. Okay. As we discussed earlier, that there is no meaning of the 6400 kilometer distance between the center of Earth and the observer on the Earth. Why? Because the celestial sphere itself is having infinite radius, and secondly, we do not have any concern with the distance between the 2 points. So, even I can bring this horizon which is passing through point P at the center of the Earth. That will make my life little easy, because I can find out what are the locations of the different stars with respect to center. With this idea, let us see, I am putting this and extending the horizon. Now, there is a horizon which is parallel to the observer's horizon, but it is passing through the center of the Earth. Okay. So, such a horizon is intersecting with the celestial sphere. Such a horizontal plane or such a circular horizontal plane which is intersecting with the celestial sphere, it is called celestial horizon. And remember that for a particular position P of observer, this is the valid celestial horizon. For another position on the surface of the Earth, its orientation will be quite different. So, for point P, this is the celestial horizon. Okay. If I extend now the line which is passing through point P and center of the earth towards both sides, it will intersect the celestial sphere at 2 points. Let us say this point and another point which is below the horizon, shown by the another yellow dot. So, these points are called zenith and nadir. Zenith is exactly above my head right now, and the nadir is exactly below my head on the celestial sphere. That is the idea here. Okay, now where is the observer? Observer is sitting at the center of the earth, where all the axes, rotation axis and the zenith nadir line, they are meeting. Now the observer can direct his eyes like this. So he can visualize all the stars, he can see all the stars, he can find out the relative angle between the two stars at the center of the earth. That means this angle it can find. If there is a one star, another star here, this angle. Also it can change its location like this to another two stars, and it can find out fine. And since this is a celestial horizon of observer, he can look around like this for the whole this 180 degree, complete hemisphere he can look around. So that is the idea of celestial horizon and how is it interacting with the celestial sphere. Okay. In similar fashion, if I extend the equator of the earth, it intersects with the celestial sphere, it will create a circle or it will create a circular plane, and that plane is called celestial equatorial plane, and the circle where the celestial equatorial plane intersects with the celestial sphere is called celestial equator. You can see the green line here, which is developed by extending the equator of the earth. So that green line or the green circle, that is containing the equator of the earth and also the center of the earth, it will create a plane. In this plane I have celestial equator of the earth and the center of the earth. So such a plane formed by the celestial equator is called celestial equatorial plane. Okay, so this is my real situation here. You can understand now easily what is the celestial sphere, what is axis of heaven, what is north celestial pole, zenith, nadir, celestial equator, celestial horizon and south celestial pole, and all these features. They are fundamental things to learn the astronomy. If you are still confused or if you want still some kind of more clarification, you can repeat this video and try to see it again. Okay, so let us go ahead. Let us try to understand the basic terminology. We have already covered what is celestial equator. We also defined what is the celestial equatorial plane, and then we also understood what is the celestial horizon, or we can also say celestial horizontal plane. We can also define that now. Okay, then we have northern and southern hemisphere. What does it mean? I can see in the last figure there is a celestial equator or celestial equatorial plane. Above this plane there is a hemisphere, I call it northern hemisphere. Okay, and below the celestial equator I call it southern hemisphere. Similarly, if I divide the celestial equator vertically, so there will be an eastern hemisphere and there will be a western hemisphere on the two sides of the vertical plane passing through the north celestial pole and south celestial pole. Well, then we have great circle and its pole. So what do you mean by great circle? I am defining any circle on the celestial sphere, but that should contain the center of the earth or the center of the celestial sphere. Then I will call it the great circle. You can imagine there are infinite number of great circles there. So celestial horizon is a great circle because it is containing the center of the earth. Celestial equator is another great circle, or if I draw any circle passing through north celestial pole or south celestial pole, it will also be a great circle because it will contain the center of the earth. I hope the definition of great circle is very clear. Okay, if I take any great circle now, so with respect to that circle, there will be 2 points which are joined by the line perpendicular to that circle. For example, axis of heaven is defining 2 poles for celestial equator. The meaning is, I have a celestial equator and then it defines the celestial equatorial plane, and with respect to that plane, if I draw a line perpendicular to that, so that will be the line passing through the center of earth, and that line will be the axis of heaven, and that has two ends, north celestial pole and south celestial pole. So NCP and SCP are the poles of celestial equator. Similarly, if I consider another great circle, that is the celestial horizon, zenith and nadir are the poles of the celestial horizon. Well, now you can imagine any circle, just close your eyes and try to imagine any circle that is containing the center of the earth, and it is subscribed or described on the surface of the celestial sphere. So that circle is great circle, and now you can imagine two poles of that circle. Okay. Further, we have a reference meridian. Remember, in case of terrestrial reference frame, we defined the Greenwich meridian as a reference meridian. In the same fashion, we can take any meridian on the surface of the celestial sphere, and then we can define it as a reference meridian. We will see how to define that. Okay. Further, we have stars meridian. Okay. Let me tell you what is the celestial meridian before we define stars meridian. The celestial meridian is a great circle that is passing through zenith, nadir, and NCP and SCP. Definitely it will contain the center of the earth. You can imagine it, or you can draw on the paper. It is also called observer's meridian. You can see this terminology in different books. Remember, they are basically same, celestial meridian and observer's meridian. Similarly, if a great circle that is passing through north celestial pole, south celestial pole, and a star, it is called stars meridian. It's very easy to understand now, because once you can imagine the celestial sphere, you can imagine the celestial horizon, and if you can imagine celestial equator, everything is very easy here. Okay. Since we are interested in angle measurement only, we need to define fundamentally two types of circles. We define the primitive circle. Okay. Primitive circle is a great circle along which I will measure one angle, and secondary is the circle which is perpendicular to the primitive circle, and again that will be great circle also. So there are two types of circle I need to define in order to measure two angles for the star. So let us see, there is a celestial sphere. This is your celestial equator, this is celestial horizon. Okay, so that is NCP, SCP. Fine, that is the axis of heaven, and that is the line joining zenith and nadir. That is what we have already seen in the last slide. That is the great circle passing through north celestial pole, zenith, south celestial pole, and nadir. So it is partly visible on the front side and partly not visible because it is on the back side. So we are drawing it by dotted line, which is not visible or which is appearing on the back side. Well, in the books you can find out this is drawn sometimes with a firm line, complete firm line, no problem. Concept is same. Okay, so this is my observer's meridian or celestial meridian. Let us see, there is a star situated on the celestial sphere. Any great circle that is passing through north celestial pole, star, and south celestial pole will be called stars meridian. The way we have defined observer's meridian, same way we will define the stars meridian. So let us see, this is the stars meridian. Okay, so celestial equator is my primitive circle. Any meridian is a great circle perpendicular to the celestial equator. So all the meridian circles are the secondaries to the celestial equator, because the celestial equator has been defined as a primitive circle. So I can measure some angle along the celestial equator. Similarly, I can measure the perpendicular to the equator also along the meridian circle. Well, that's the idea here. That means I can define two-dimensional position of a star. Okay, so I have given an example of celestial equator as a primitive circle. Even I can take the celestial horizon as a primitive circle. Well, I hope that you are appreciating these simple concepts. They are very simple. Some kind of visualization is required, and I hope that these graphical aids are able to help you to visualize those things. Let us move ahead. So this is my stars meridian. So we are going to use this kind of two perpendicular circles, and now we are going to derive those circles in different manners. and accordingly we are going to say we have different reference system to measure the position of a star. And finally, we will come to a inertial reference system, but before that we need to understand how to connect that reference system to our understanding or to our measurements. Let us start. Let us see horizon reference system. Okay. So, primitive circle is my celestial horizon. Remember, celestial horizon is different from celestial equator, and celestial horizon depends on the observer's position. So, as observer's position changes, celestial horizon will change, but equator is not going to change. So, vertical line, as we know that plumb line meets the celestial horizon. Then we have poles. With respect to celestial horizon, I have two poles, zenith and nadir, because they are lying on the vertical line which is perpendicular to the celestial horizon. Okay. Secondaries are the vertical circles. So, what are the vertical circles? So, any great circle which is passing through zenith and nadir is a vertical circle, right. So, vertical circle is obviously perpendicular to the celestial horizon. Circles which are parallel to the celestial horizon are called parallel of altitude, or they are also called almucenters, right. And then we have meridian line and noon line, we will see in the animation here. Okay. This is the standard animation we started with. Okay. Now, this is celestial horizon, celestial equator, zenith, nadir. Let us rotate it for simplicity to understand horizon reference system. Okay. So, now my horizon is horizontal, or in this screen it is becoming more convenient to me to understand. So, now I am having my celestial equator tilted. Okay, no problem. So, I am going to measure altitude and azimuth in horizon reference system. Remember, we are using the term reference system because it is just a concept now, we have not realized it. Okay. So, measurements in the horizon reference system are azimuth and altitude. What is azimuth? Azimuth, as you know from our standard definition, it is the angle measured in the celestial horizon from the astronomic north. Remember, we are not talking about any other north like magnetic north or geographical or nothing. We are talking about astronomic north. So, this is the azimuth. Then altitude, any angle measured perpendicular to the celestial horizon, it is altitude of a star or of any point on the celestial sphere. I hope it is very easy, you can imagine it very easily. So, altitude is positive for the elevated points which are above celestial horizon, and negative for points of depression, the point which is below the celestial horizon. Okay. So, now we define a term. The zenith angle is complementary angle of altitude, that is 90 minus alpha if alpha is altitude. Okay. So, for a point of depression, I can see that altitude angle will be negative. So, the complementary angle which is co-altitude or zenith angle or zenith distance will be more than 90. What about the dependencies on the altitude and azimuth of a star? As we assume that Earth is stationary and all stars are moving, altitude and azimuth depend on time. Not only that, both altitude and azimuth also depend on the observer's location. So, at a given instant, at my location and your location, I will have different altitude and azimuth of a star, for example, sun. At one position on the surface of Earth, if I vary the time, that means if I am observing sun at this moment and I observe the sun again after a couple of minutes or couple of hours, the position of sun will change. So, the altitude and azimuth depend upon not only the time, but the observer's location. We need to connect it to the celestial reference system, which we have not established yet. So, let us go ahead then and see how can we connect this horizon reference system in which we generally perform a measurement, that is the altitude and azimuth. And now, how to connect that azimuth and altitude angle to the other reference system? Now, we define dependent reference system. As we see that azimuth and altitude in horizon reference system are changing with time as well as changing with observer position. Okay. Moreover, in time I would like to specify there are two type of time. One is the annual time, that is 1 year, and another is daily time, that is 24 hours. So, I can say the observer's position is changing with respect to time So let us look into the different system called dependent reference system. So the primitive circle here is celestial equator. So celestial equator is also called equinoctial. So now you can imagine that meridians which are passing through NCP, SCP and their great circles will be the secondaries to the celestial equator. Okay, these secondaries are also called circles of declination or hour circles. So now if I draw any circle which is parallel to the equator, it is called parallel of declination, and we define the angle declination and hour angle with respect to equator and circles of declination or hour circles. Let us see how do we do it. I am not reading this thing, rather I am going to show in the animation. Okay, that is my celestial sphere, celestial equator. So this is my NCP and SCP. So let us see, this is the celestial horizon of an observer, and now zenith and nadir are like this. Okay, so this is my celestial meridian, north and south point, as we have already defined all this thing. I am not doing anything new now. Here, this is one of the circle of declination or hour circle. So this is the parallel of declination, which is parallel to celestial equator. Okay, just for the purpose of introduction, we introduced two things. Now we are removing it like this, and now let us see, there is a star here at this given instant. Okay, so this is my star's meridian. We have already defined celestial meridian, you see, and now this is star's meridian. Okay, so you can imagine that celestial equator is primitive circle and star's meridian will be one of the secondary. Similarly, celestial meridian itself is one of the secondary. I hope you can easily understand it. An angle measured perpendicular to the equator and up to the star along the circle of declination is called declination. This angle, see declination, and again I am showing the white color like this. So this is declination. Okay. Similarly, I have this angle which is called co-declination, right, and it is 90 degree minus delta. So if a star is below equator, 90 minus delta will be 90 plus delta, because delta will be negative. Now what about the hour angle? Hour angle is little tricky to understand. First of all, we are going to measure the hour angle in the plane of celestial equator. And let us look how to measure it, and it is always measured with the help of or with reference to or with respect to celestial meridian of observer. So now you can see that celestial meridian is cutting or it is intersecting in 2 points with celestial equator. One is on the left hand side, one is on the right hand side in the screen. Which point should I take to measure the hour angle? The key here is take a point which is above the celestial horizon. That means the reference point is on the celestial equator, but the point is above the celestial horizon of the observer. In the screen it is on my right hand side. So if I draw the line which is connecting the intersecting points of celestial meridian and celestial equator. As I told, I am going to take a point in celestial equator which is above the celestial horizon. So now I am going to show you the hour angle in the celestial equator. So this is the hour angle measured here in the animation. Just try to relook if you do not understand. Again, I am going to show in the white color also. This is my hour angle h, and this is again my hour angle h. They are same. Also, this is my hour angle. Again, on the NCP I can see this is hour angle h, right. I hope you understood the concept of hour angle and declination. What about the annual motion of the earth? Well, in the yearly motion or the revolution or orbit of the earth around the sun, the center of mass is also going to shift in the space, since it is not a horizontal path around the sun that we are going to see in the coming slides. So the declination will be changing not over the day, or rather it will change over the day very small quantity, but it is definitely going to change over the year. So every month if you see the ephemerides, the stars catalog, you will find out that declination is going to change even every moment, I can say, but the change is not that rapid. But if you see the values of declination over the every month, they will be changing, because during a month earth is going to revolve also, but In a day it revolves, yes it revolves, but very small amount. So now we understood the concept of hour angle and declination. So here again I am writing the dependencies. The circle of declination do not change with rotation of earth. So declination does not depend by daily motion, that is the diurnal motion or spin of earth. Declination does not change with observer's location also. So it is independent of time. Which time? Spin time, not the annual time, right? Secondly, coming to the hour angle, observer's location, it is changing every moment, and as a result hour angle is going to change every moment. But if you see carefully, on a given celestial meridian, even latitude is changing, but hour angle will remain same. That means hour angle does not depend on the latitude of a place, rather it depends on the longitude of the place. Okay, if you remember carefully, with respect to equator, we have also measured the longitude and latitude in terrestrial reference frame. So if you recall, in astronomic coordinate system, we have reduced astronomical longitude and a reduced astronomical latitude. We are talking about those latitude and longitude. Remember, we are going to use those here. And very surprisingly, we will connect with our reduced astronomic latitude and longitude of a place to the declination, right ascension and hour angle and so on. All these variables we are going to connect, and even azimuth and altitude of a star. Fine. Let us develop our further understanding in the subject. So, as I told you, hour angle changes with the reduced longitude or reduced astronomic longitude of a place, and it is changing every moment. Definitely, it is going to change every week and every month. So, it is going to change annually, it is going to change daily, it is going to change every moment, and it is also going to change with respect to the observer's position. Well, so now we have derived the declination which does not depend on the observer's location. So, irrespective of the observer's location, for a given star, declination will remain same over a short period of daily path, 24 hours, something like that. So now I define a term co-declination and polar distance P, which is 90 minus delta, and south polar distance become 90 plus delta if point is below equator. Moreover, we have defined hour angle. I repeat that hour angle changes every moment, every instant. So hour angle of star for a given celestial meridian or observer's location is going to change, and that is why we can see that sun changes the hour angle every moment. Now we define an independent reference system. What do you mean by independent reference system? Remember, hour angle was still dependent on the observer's location. So let us define a quantity like hour angle which does not depend on the location of observer, because declination itself is independent of observer's location. And now we define such quantity as a right ascension, which is similar to hour angle, but it does not depend on the observer's location. So what do we do for that? Okay, we find a point on the celestial equator which remain fixed and which does not change over the time. Okay, so let us define a point called vernal equinox, which is the intersection of ecliptic, the relative path of the sun. And this path of the sun does not depend on the daily motion of the earth. If we see the annual path of the sun around the earth, that will intersect at one point, and that point we call vernal equinox. If you can imagine, it will also intersect with another equinox called autumnal equinox. At the vernal equinox, sun ascends from southern hemisphere to northern hemisphere, and this date is around 21st March in a year. Okay. Similarly, autumnal equinox, where sun descends from northern hemisphere to southern hemisphere on its annual path, not on the daily path, right? And that comes around 21st September. So there is a vernal equinox a point. Now with respect to that, we will measure an angle, we call it a right ascension. So let us look into the animation to understand what is right ascension and declination. Okay, that is my celestial sphere. On celestial equator is shown here. So that is the NCP in SCP. That is my celestial horizon, and we have deliberately tilted it in order to explain the concept of right ascension. So this is the zenith nadir, and this is the celestial meridian. So till this point concepts are same. This is the north and south on the celestial horizon, and east and west are also shown. So, let us say this is the ecliptic or the annual path of the sun, or sun is apparently moving around earth annually on this path shown by the red color or red dotted line. So, the intersection of the celestial equator and the ecliptic is called vernal equinox, and so the point shown by the black dot here is our vernal equinox, written by this symbol, right, and this symbol is very special here. It is written like this, and vernal equinox is also called the first point of Aries. So, now let us say there is a star here and this is the star's meridian, okay, and let us say there is a meridian of vernal equinox passing through the vernal equinox. So, we have defined the meridian of vernal equinox. Now, I want to measure right ascension from the vernal equinox to the star's meridian. So, let us connect the star from the center of earth and with equatorial plane. So, like this, let us draw these two lines, and this angle you already know that this angle is declination. So, this is my declination angle, right. So, now let us define the right ascension. The right ascension is the angle between the vernal equinox to the star's meridian, but measured in the plane of celestial equator. So, if I connect the center of earth to the vernal equinox, this will be the line. Now, if I measure this angle, right ascension of the star. Okay, it is very clear from the animation how to measure the right ascension and how to measure the declination. But if you see carefully, that right ascension is measured opposite to the hour angle, or rather hour angle is measured from the point on celestial equator which is above south of celestial horizon. We measure the hour angle positive in the westward direction or in the direction of the movement of the stars. However, right ascension is measured eastward or opposite to hour angle or in the direction of terrestrial longitude. Well, terrestrial longitude, what we call reduced astronomical longitude. Now, it is very clear to you that the right ascension, since it is measured from the vernal equinox, it is very much independent of the observer's position, because the vernal equinox itself is a reference point now, and the vernal equinox is not decided by the observer's position. We have derived a reference system and two coordinates, right ascension and declination, both are independent of observer's position. Moreover, I can say that vernal equinox itself does not depend on the rotation of the earth. So, we can say that the right ascension and declination both are independent of the rotation of the earth. So, what about the hour angle? In this animation, let us look into the hour angle. This is the hour angle of the star and HS. So, this is also HS. Okay. What about the hour angle of vernal equinox? So, this is the hour angle of vernal equinox. Fine. You can see here very carefully that if I want to measure the hour angle of vernal equinox, I can measure it as a summation of hour angle of star and right ascension of the star. That means, if I want to find out what is the hour angle of vernal equinox, it is summation of the hour angle of star, which is my HS, and the right ascension of the star. So, I can write here this terms you can see here in the graphics or the animation. What about the dependencies of the right ascension and declination? As we have already told that declination is independent of the rotation of the earth. Due to the rotation of the earth, the equatorial plane of the earth is not going to change its position, and that is the reason declination is independent of the rotation or the rotational time of earth. Now, what about the right ascension? Right ascension is measured with respect to the vernal equinox, and the vernal equinox itself is defined in a way that is independent of the rotation of earth. Remember, vernal equinox is the intersection of ecliptic and celestial equator. So, both ecliptic and the celestial equator does not depend on the rotation of the earth. I hope that you got the concept that why right ascension and declination are not only independent of observer's position, also they are independent of the rotation time or the daily spin of the earth. But what about the annual motion of earth? So far we have not discussed about the annual motion. Due to the annual motion of the earth, the position of the celestial equator or the equatorial plane of earth also varies, because earth is moving around sun in the ecliptic, and as a result they change significantly over the year or the annual motion of the earth. So, we should be very careful on these concepts. Can we derive coordinates which are also independent of rotation time or annual time as well as the position of the observer? So, let us devise that. So, now we introduce a new system called celestial reference system, and the full name is celestial longitude and latitude system, where we measure the celestial latitude and celestial longitude. So, let us look into the animation. What do we mean by celestial latitude and celestial longitude? That is celestial equator and celestial sphere, fine. NCP, SCP, again the celestial horizon, Zenith Nadir, celestial meridian, okay. So, that is my south, east, west, north on the celestial horizon. Then this is my ecliptic, and so this is the vernal equinox, fine, okay. So, that is the meridian of vernal equinox, and that is a star. I want to measure two coordinates of the star which are independent of the any time of earth, either it is rotation or daily spin or it is annual motion of the earth. So, how can I do it? Now, let us look into the animation. So, I have star's meridian. So, if I connect the center of the celestial sphere to the star's meridian, it will be this line, right. So, let us connect the center of celestial sphere to the star, okay. Then we have framed an angle, you can see here in the animation. So, this is my celestial latitude. Now, this angle which is measured in the plane of ecliptic from the vernal equinox to star's meridian is called celestial longitude. So, this angle is celestial longitude. Remember that both celestial longitude and latitude are independent in a sense, because the vernal equinox is independent of time, both annual time as well as daily time, right. Now, I am measuring some angle called celestial longitude with respect to vernal equinox. It should be independent. Moreover, this angle celestial longitude is measured in the plane of ecliptic, not in the equator. So, ecliptic itself is independent of earth motion. So, as a result, now I can define the star's position using celestial latitude and celestial longitude. This position will be independent of the earth's rotation, earth's position and earth's motion. So, let us make a summary of our learning today. So, we have astronomical reference systems and we have defined 4 types of reference systems. So, first is horizon reference system, then we have dependent equatorial reference system, then we have independent equatorial reference system, and then we have celestial longitude and latitude system. Here, in case of horizon reference system, we measure the position of a star as azimuth and altitude. In dependent equatorial reference system, we measure the position of star by hour angle and declination. In case of independent equatorial reference system, we measure the position of the star by right ascension and declination. And finally, in celestial longitude and latitude system, we measure the celestial longitude and celestial latitude of a star. And celestial latitude and celestial longitude are independent of any time or any motion of earth, as well as the observer's position. In case of right ascension and declination, we know that both right ascension and declination are also independent of the rotation motion or the daily rotation of earth, as well as they are independent of observer's position. Now, what about the hour angle and declination? As we say that hour angle depends on the celestial meridian, or observer's position, but only in the longitude of the observer's position and not on the latitude. Okay, what about the azimuth and altitude? Both azimuth and altitude depend on the time as well as observer's position. We can see here that all these 4 reference systems are using 2D angular coordinate system and what we call as geographical coordinate system. So, this is the total learning we have done today. In the next lecture, we will see the applications of these reference system.